I want to get to solving problems and my strategy for using conservation of energy. So let's take an example, like a roller coaster or something. So maybe something like this, where perhaps we have a cart with a certain mass and initial speed, and it's going to go over this first hill down here. And it should have some new speed down here. So I want to come up with some sort of relationship that will allow me to solve for different variables. And what we're going to do is create bar charts. So we're going to have one set of bar charts for the top of the hill. We're going to have one set of bar charts for the bottom of the hill. You'll hear teachers talk about these, or they'll describe these as LOL charts. And that's because we draw a circle in the middle. So the circle here is just to let everybody know what our system is. And I'm going to define this as a system with the cart in there, because since it's moving, it will give us our kinetic energy. To have some potential in there, it'd be nice to have a field probably. So in this case, since we're changing heights, I want to work with a gravitational field. So I'm going to add in a second object. We're going to say cart and Earth system. So cart, Earth, that's our system. This bar chart will represent the energy at the top of the hill. This energy will represent this bar chart will represent the energy at the bottom of that little valley. So we're going to have kinetic, translational, we're not dealing with rotational, gravitational, elastic, and we'll set that up over here. We may want to leave a spot for like work that's done, and we'll want to keep track of the mechanical energy as a whole. So what we need to do is kind of go through this and identify what we have. The cart is moving, so we know we have some translational energy, translational kinetic energy. It's not really rotating. We can consider maybe that the wheels, if there's a cart, if there are wheels on this cart, maybe that rotational motion is negligible. So I'm going to go ahead and mark 0 here. Gravitationally speaking, well, what do we want to make 0? Do we want to make it the start of the coaster? Do we want to make it the lowest point of the coaster? Do we want to make it the highest? I'm going to go ahead and say it's the start here. So it has plenty of gravitational, and it's not really stretching or compressing, so we have no elastic. So when we add up our kinetics and potentials, we get our mechanical. So it's currently made up of translational kinetic energy and gravitational potential energy. Down at the bottom, the cart we're still saying has negligible rotational kinetic energy. It's not really stretching or compressing, but it's become lower And I can't remember if I set the bottom as 0, the middle as 0, or the top as 0. If I set the middle here at the initial point as 0, this is below it, so we would have negative gravitational potential energy. If I set here as 0, we would have none. In either case, our gravitational potential energy has gone down. So let's just work with that, that the gravitational potential energy has gone down somehow. So it's now less. If there's no friction along this coaster with the cart, there's no work being done. So if there's no dissipative forces, our mechanical energy should still stay the same. But if our gravitational is taking up a smaller amount, that means our kinetic has to take up a larger amount. So we can see that the cart has gained speed. Now let's say we didn't have the Earth in our system. No Earth. I'm not saying that the Earth, well, I'm not saying that the Earth is gone. I'm just saying that the Earth is not considered part of the system that we are measuring. In that case, we wouldn't have this gravitational potential energy because the Earth isn't there the Earth is still there, but we're not considering it part of a system, so it's actually an external source of energy. In that case, it's doing work, and our LOL chart would be a bit different. So somehow this cart's gaining energy, but we're not considering gravitational potential energy anymore. That means there had to be some work done. In that case, gravity did the work, and we ended up increasing our mechanical energy. Since there is no potential, our mechanical energy is solely the kinetic. So that's the difference between having something in your system and something outside the system. Because we made the Earth external, then our energy, our mechanical energy, wasn't even conserved. So let's go back to our original setup. And why do we make this LOL chart? What's the point? Well, if I know that the mechanical energy is conserved, I can say, okay, mechanical energy at the beginning equal to mechanical energy at the end. I can see that it's made up of translational kinetic energy and gravitational potential energy at the beginning and at the end. And I now can set up a relationship that lets me solve for stuff. So 1/2 mv naught squared plus mg h naught is equal to 1/2 mv squared plus mgh, or y, whatever you want to use. I would, if this was like a free response, I would stick with whatever variables they give you. And you'll notice the masses would cancel, and I can multiply everything by 2, so I get v naught squared plus 2g h naught is equal to mv squared plus 2gh, and this is starting to look, whoops, left the m in there. This is starting to look familiar. This is our kinematics equation. The masses don't always cancel, especially if we have a potential energy in there. that is like elastic, or something that doesn't depend on mass. And that's essentially how I kind of want you guys to solve conservation of energy problems. Set up your bar charts. Make sure to include work, your mechanical energies. If you want to, you can even keep track of your total energy. And I can show you why that's important. If we look back at the system here, if we had friction acting against the cart the whole time, so it doesn't matter where the cart is, the friction would always be acting parallel to the surface, so it would always be doing work. It would slow down that cart the whole way, so it would be doing negative work. Well, that amount of work that's being done would decrease our mechanical energy, and that's got to come from somewhere. It's got to come from the kinetic or the potential. The potential is based off the height, and the height hasn't changed. So that tells us that we have to see that same drop in our kinetic. So the coaster would be going slower. But what about our total energy? Well, that should stay the same if our system's isolated. So this could be going into heating the track, so its internal energy goes up, or heating the cart, so its internal energy increases. If it goes outside the system between cart and earth, so I guess, yeah, the track, if we consider that outside the system, that would be lost energy. So we'd lose some there. If it became sound, and that would be a loss of energy that's lost to the air, to us. So it kind of depends on where that energy is going. But we shouldn't lose energy if we make our system inclusive enough. Okay. And that's all I got.